If I have a moving charge and there is a magnetic field available in space, this magnetic field can produce a force over the moving charge. But before talking about this force, let me quickly remind you about the magnet and talk a little bit about the magnetic force. If I have a magnet, usually we assign north pole and south pole for both ends of this magnet. Magnetic field is the field produced by this kind of the material, and there are lines similar to electric field lines which are coming out of the north pole and going toward the south pole. So if I want to show magnetic field produced by this magnet, they kind of look like this. So here, as I mentioned, the direction of the arrows for this magnetic field would be from the north pole toward the south pole. If I get away from the poles, the magnetic field strength becomes smaller and smaller, but if you get closer to the poles, the magnetic field strength becomes greater. So now imagine we have some magnetic field produced by a magnet, for example, in space, and we have a moving charge which is traveling in space, and we want to see what is the force acting on that moving charge. We know that force is a vector, so we can talk about the direction of this force and the magnitude of this force. Let me first show you how we can find the magnitude or size of this force, and then I will tell you how we can find the direction of the force acting over the particle as well. The size of the force could be found using this equation, which is Q VB sine alpha. I have mentioned what are the names of each of the variables we have here. So Q is the charge of the particle, V is the speed of the moving particle, B is the strength of the magnetic field, which is usually given to you in Tesla. So Tesla is the standard unit we have for the magnetic field. And finally, alpha is the angle between the direction of the motion of particle, which is along this velocity, and the magnetic field in space. For example, if this is the magnetic field, B, and this is the direction of the motion of the particle or its velocity, angle alpha would be the angle between these two vectors. So there are a few things we can immediately understand by looking at this equation. For example, we need to have definitely a moving charge in order to have some magnetic force acting over the particle. Because if I have a stationary charge, V would be 0, and that makes the force to be 0. So there is no force over stationary charges. No matter how strong is the magnetic field, if the particle is stationary and doesn't move, there is no force over that one. This is a really important statement that you can get immediately from this formula. The other thing we can say is that there are certain angles for which sine would be equal to 0. Those angles are alpha equal to 0 or alpha equal to pi. So if I set alpha to be 0 or pi, then in that case sine alpha becomes 0, and that makes the force to be equal to 0. What's the meaning of that? Remember that alpha was the angle between the magnetic field and the direction of the motion. If this angle is 0, it means that both velocity and magnetic field are going to point along the same direction, and when the angle is pi, it means that magnetic field and the direction of the motion will be opposite to each other because they make the angle of the 180 with respect to each other. Based on what we found earlier, in both cases, when the particle is moving along the magnetic field or the particle moving against magnetic field, this angle is going to make sine to be 0, and as a result there is no force acting over the particle. So that's giving me the second important statement. No force over moving particle along or opposite to magnetic field B. So in both cases, there is no force acting over the particle. Now let's talk about the direction of this force. Direction of the force acting over the moving charge could be found using right-hand rule. So right-hand rule is the method we use to find what is the direction of the force. And the right-hand rule I'm going to talk about here would be specific for this formula when I have F to be equal to Q VB sine alpha. Okay, let's see how we can understand this right-hand rule. There are two different ways we can talk about this right-hand rule. So in one of these methods, I can say that I use my right hand and put my fingers along the vector v, the first vector you see in this equation. And then I try to bend the fingers of my right hand toward the second vector, which is magnetic field B, and then my thumb shows the direction of the force. This is kind of shown in this picture here, that if you put your fingers of your right hand along the V vector and bend your fingers toward the magnetic field direction, then your thumb shows the force. For example, let's look at this picture here. Imagine I'm looking for the positive particle, which is shown by the red color. This positive particle is getting into the magnetic field from left to right. So at the initial moment, this is the velocity of the particle. The crosses shown in this picture determines the direction of the magnetic field we have in a space. Because magnetic field itself is a vector, we can have the magnetic field pointing into the page or out of the page as well. So we have a certain notation for these magnetic fields. If magnetic field is pointing out of the page, we're going to show it by a dot. And if it's pointing into the page, we're going to show magnetic field by a cross. So because here we have crosses in the picture, it means that the magnetic field is pointing into the page. Okay, so let's look at this picture and try to use the right-hand rule I explained earlier to predict what is the direction of the force acting over this particle, which is entering this region with the magnetic field from left to right. So velocity will be toward right, magnetic field will be into the picture. What I do, I try to use the right hand, put the fingers along the first vector, which is V, and then I try to bend my fingers toward the second vector, which is magnetic field pointing into the page. So if you repeat that, this kind of the right-hand rule, you can see that your thumb is going to point upward in the screen. So it means that the direction of the force is going to be in this direction. That's why, if you look at this picture, after the positive particle getting into the region, it's going to push upward and it's going to move over this kind of the circular path shown in the picture. But but there is another important point I have to emphasize here. The right-hand rule we describe here only works for positive particles. If I have a negative particle, we need to switch the result of the right-hand rule. For example, if from the right-hand rule you get the force to be upward, for the negative particle it's going to be downward. If using right-hand rule you found that direction of the force would be toward right, for the negative particle it's going to be toward left. So whatever you get from the right-hand rule should be flipped if you have a negatively charged particle. That's a really important point. That's why if you look at the picture again, so here I have also a negatively charged particle which is entering into the this region along the same direction. So we have same V direction. However, as you can see, this negative particle is bent downward. So it means that the force acting on that would be pointing down. The reason is that if I use the right-hand rule again, start with the vector V and bend my fingers toward the vector B into the page, my thumb shows upward, but because I have a negative particle, I need to flip the result. That's why the actual force over this negative particle would be pointing downward. So immediately you can see from this simple argument that if I have charges with opposite signs and send them into the magnetic field, they're going to be split immediately because the positive one and negative one are going to follow different paths because the force acting on them would be different and opposite to each other. Okay, let's talk about the second version of the right-hand rule as well. The second version of the right-hand rule, which I explained it here, works in a similar way. So in this method, what we do, we try to put the fingers of the right hand along B vector, magnetic field. And also, you put your thumb along the direction of the motion of the particle or velocity. And then your palm shows the direction of the force. Let's do it here as well. For example, in the same picture for the positive particle, we know that the magnetic field is pointing into the page. And the velocity direction would be toward right. So you have to put the fingers of your right hand into the page while your thumb is pointing toward right. If you repeat this kind of the right-hand rule, you will see that the magnetic force is coming out of your palm. So that would be, again, upward force for the positive particle. Similar to what I mentioned before, if I have a negatively charged particle, in that case, we need to flip the result of the right-hand rule. That's true for both of these versions of the right-hand rule. So if I want to give you a schematic picture for the second version of the right-hand rule, so use the right hand So I just try to do my best. It's the right hand. So I put the fingers along B while my thumb is toward V. And then here, the magnetic force coming out of your palm. So here, this is the force. Okay, now let's look at this force in a little bit more detail. We just mentioned that if I have a particle getting into the region with the magnetic field, there's going to be a force acting on that. I want to look at this scenario more carefully and specifically look at the case when the velocity of the particle would be perpendicular to the magnetic field, similar to what we showed in the previous picture. Even in this picture I have here, the magnetic field is pointing into the page because we have crosses here. And then I consider the positive particle moving upward because the velocity shown here is pointing upward. So let's quickly apply the right-hand rule and find direction of the force. So here we have a positive particle, so we can use the original right-hand rule. If I use the first version of the right-hand rule, I put the fingers along velocity, which is pointing upward, bend my fingers toward the magnetic field, which is into the page, and my thumb is pointing toward left. That's why the force is going to point toward left. That's why the particle moving to upward is going to bend a little bit toward left because of this force. If I look at the new position of the particle, the velocity would be still tangent or parallel to the path. And then if I repeat the right-hand rule, you can show that the force this time is going to point in this direction. Notice that force would be always perpendicular to both magnetic field and velocity vector. That's going to bend the particle a little bit more, and that's why if I look at the velocity in another moment, it's going to be bent a little bit more. And again, if I repeat the right-hand rule, you see that the force is going to point toward the center. That's why if I look at the path traveled by the particle is going to be a circle. So in this case, because I had the positive particle, initial force was toward left, and that start to bend the particle toward left. That's why here we have a counterclockwise circle. Now you can guess immediately that if instead of this positive particle, we had a negative particle with the same velocity, because the result of the right-hand rule would be opposite for the negative particles, in that case, the force acting over this negative particle was toward right, and it was bending the particle toward right. That's why in that case, we had a negative particle moving in a clockwise direction. So what we see here is that if I send a bunch of particles into the magnetic field, and such that the direction of the motion is perpendicular to the magnetic field, the positive particles and negative particles are going to move over circles. However, these circles are going to have opposite directions. If one of them is clockwise, the other charge should be counterclockwise. Furthermore, we can also talk about the radius of this circle. We just need to remember basics of the circular motion. Let me explain how we can find the radius. In this case, we know that the size of the force would be equal to QVB sine alpha, when Q is the charge, V is the speed, and B is the magnetic field strength. And remember that alpha was the angle between the magnetic field and the direction of the motion. Because I consider V to be perpendicular to B, this angle would be 90 degrees, and sine of the 90 would be equal to 1. So in this simple case, F would be QV times B. Furthermore, we remember that for the circular motion, we can write down F to be ma, when A would be the centripetal acceleration equal to V squared over R. So here V would be speed again, and R is the radius. By combining these two equations, I can write down QVB to be equal to mv squared over R, and after simplifying one of the V's on both sides, we can find radius R to be mv divided by QB. This is the radius of the circle for the path traveled by the particles if they get into the magnetic field perpendicular to the magnetic field in space. Let's analyze this equation a little bit more to understand it better. Notice that this radius is directly proportional to the mass. If I have a heavier mass, we expect to have larger radius. Because it's harder for the force to bend this heavier mass, we're going to generate a larger radius. So similarly, if I have larger speed for the particle, we're going to have greater radius. The reason is that, again, till the force is going to bend the particle, so it's that already traveled a longer distance. That's why we're going to have a larger radius or bigger circle. But opposite to these two variables, radius is inversely proportional to Q and B. If I increase the charge, I'm going to increase the size of the force. That's why stronger force is going to bend it faster. As a result, we have a smaller circle or a smaller radius. Similarly, a greater B value means that we have a stronger magnetic field, and that generates a stronger force over the particle. Again, it's going to bend it faster, and we're going to have a smaller circle with a smaller radius. The formula we found for the radius will be the same for both positive and negative particles. That's why it's better to put absolute value of the charge here to make sure that we always get a positive number for the radius.